In this video, I'm going to go over the Unit 5 Section 1 notes, Part 1, on kinetic molecular theory, an introduction into gases, and the variables we will use in this unit. So first, as mentioned, we'll go into kinetic molecular theory. I'll talk briefly about solids and liquids, but we'll really focus on gases for this unit. We'll then talk a bit about variables that we'll use to define those gases. Primarily, we'll focus on pressure in this presentation. We'll talk briefly about volume and number of particles, as well as their effect on pressure. We'll have a bit of a discussion on temperature, and we'll end with something called STP. Without further ado, let's get into it. So first, kinetic molecular theory is the idea that all particles in any substance, whether it's atoms or molecules, they're constantly in motion. So for instance, if I look at a solid material and I could zoom in on those atoms or those molecules in the solid, I would see that they are all essentially vibrating in place. They're bound to one another through some form of bonding, be it ionic or covalent or some other type of force, but they're basically vibrating in place. If I look at a liquid, the particles are still attracted to one another, but they can flow past one another. They have more energy, enough to flow past all the other particles around them. And gases, what we'll focus on for this unit, are where the particles, again, atoms or molecules, basically bounce around randomly. They'll hit each other and kind of act like pool balls bouncing around the table, and they'll bounce off the walls of the container. Kinetic molecular theory is mostly focused on gases to really define how particles move. So as mentioned, we're going to focus on gases, and a few of the pieces of kinetic molecular theory that we're going to assume is that gases have many, many particles that are very spread apart. We'll talk about amounts of particles later on. We'll assume that the gas particles are constantly moving in basically random directions. And we'll assume the piece in bold here that gas particles aren't attracted to either one another, so they're not attracted to other particles, and they're not attracted to the container itself. And we refer to this as an ideal gas, where there is no attraction between particles. We're also going to assume that the average kinetic energy of the gas is dependent on those particles' temperature. We'll talk more about that in a later slide. So as mentioned, we're going to deal with a couple of different variables in this unit. Everything we deal with will be with gases for the most part, but we will have 4 different variables and they will have different units. First, we'll deal with pressure, and there are many units of pressure that we'll talk about in just a moment. You'll deal with some in your everyday life. In this unit, we're going to focus on one specific unit to standardize things. We also have to talk about temperature. We will always keep this in something called Kelvin, which is slightly different than Celsius or Fahrenheit, and I'll show the relationship of that in just a bit. We will deal with volume, how big something is. That, in our case, will always be in liters, and I will always give that in liters, abbreviated as an L. And we also have to think about the number of particles in our gas, which we will define as moles. And we're going to use this lowercase letter n to symbolize number of particles. And as should be obvious, the units will always be mole or moles to show the number of particles, just like it was in our unit on stoichiometry. So first, let's talk about pressure. Pressure is not just with gas, but really with anything. It's the force exerted on a surface area of an object. So it's basically how much that gas or whatever is pressing over a given area. So it's not just how hard is it pressing, it's how hard is that thing pressing over a certain amount of space. For instance, the reason we use a knife to cut as opposed to using a spoon to cut something like a steak is because that knife is very sharp. It has a small surface area. So even though in both cases the force is probably similar, those people are pushing down with their hands, because a knife has a smaller area, it's sharper, the pressure is much, much higher. The same is true for gases. Except gas pressure is a little different than with solids. Gas pressure is what happens when all of the gas particles rapidly hit the surface of the container. So if we look at this atom or molecule down here, it hits the surface of the container with a force. But overall, we can't really measure one atom hitting a surface. Instead, we feel the effects of all of the particles hitting a surface, and we define that as the gas pressure. For instance, if you say feel the wind on your skin, you don't feel individual gas molecules hitting your skin, you feel the overall pressure. You just feel like a mass force against you, and that is the pressure of those molecules of air hitting your skin. So, when it comes to pressure, we're actually going to kind of use this to talk about two of our other variables. First, let's talk about volume. Notice in this condition on the left, the volume is a lot bigger than the volume on the right. The volume on the right looks about half as big. As volume gets smaller, the pressure of our gas is going to increase because we have more collisions with the wall of this container. Because those gas particles are basically smushed together, they're going to more often hit the sides of the container. So therefore, they'll have a higher pressure. Similarly, with the number of particles, if we say have a situation with a small amount of particles and a situation with a large amount of particles, as the number of particles increases, the pressure will increase as well for the same reason. There will be more particle collisions with the container walls. And that's basically what pressure is, or how we can model pressure. If there are more particles hitting the walls, the pressure will go higher. And if there are less, the pressure will go lower. So let's talk about that with relation to temperature. We have one more note on pressure. Pressure has many different units. In your daily life, you may see pressure expressed as PSI, or pounds per square inch. We use this a lot in like tires, say, or inflatable objects. You may also see mmHg, or millimeters of mercury. This is sometimes used in blood pressure cuffs or in medicine, and sometimes to relate to weather conditions. And you may also see kilopascals, or kPa. This is oftentimes used in a lot of the engineerings, especially engineerings dealing with solid materials. However, we are going to deal with one unit of pressure in this unit. We're going to stick with the unit of pressure called atmospheres, abbreviated ATM. This is used in different sciences as well as in weather applications. And basically what this is it's the gas pressure of the air at ground level. We say that at ground level, there is 1 ATM of pressure. And you might notice this picture here that shows all of these gas particles stacked on top of one another. And what this is showing is that at high altitudes, high up in the atmosphere, there are less gas particles, and so the pressure should be lower for the reasons we talked about earlier. But as those gas particles stand on top of one another, they basically squeeze the gas particles closer together when they're closer to the Earth's surface, resulting in a higher pressure, which, like I said, we define as 1 atmosphere, or 1 ATM. So your first practice for this unit is to do a bunch of pressure conversions. You'll notice that each row corresponds to one place on Earth. And you'll notice that only one unit of pressure is given. For instance, at the top of Mount Everest, the pressure in millimeters of mercury is 252.8. So I'm going to run through this first scenario of top of Mount Everest to show you how to do this. First, you'll take millimeters of mercury over 1, that amount we know, and we'll use dimensional analysis just like we have in the past to convert between millimeters of mercury and 1 ATM. Notice that I set this up so my millimeters of mercury cancel, and I'm left with ATM. And also notice that I use my relative equivalent values. 1 ATM is equal to 760 millimeters of mercury, so I set up my conversion as 1 ATM over 760 millimeters of mercury. The units of millimeters of mercury cancel, and we'd be left with 0.33 ATM as that pressure. We might as well take this value in ATM and do the same thing. 1 ATM is equal to 14.696 psi. Those units of ATM cancel, and we're left with 4.894 psi. That pressure is equivalent to the other two in the table. Finally, let's convert from psi to kPa. Set it up so your units cancel. Make sure you have 14.696 psi, which is equal to 101.325 kilopascals. Cancel out psi, and you're left with 33.743 kilopascals. And that's the pressure at the top of Mount Everest in kilopascals. Now let's head on over to temperature. Temperature is the average kinetic energy of all of the atoms or molecules in a material. Now, kinetic energy is actually related to both the mass and the speed or velocity of those particles. So both mass and speed affect temperature. If we look at this image here of these gas particles moving around, you can see they're moving at various speeds. For us, it's enough to remember that temperature is basically equivalent to speed. The faster something is, the higher the temperature. But do know that technically temperature is also related to how massive those particles are. Now, one thing I want you to note is that not all of these particles move at the same speed. You'll find that in a cold material, some particles move at relatively low speeds, but technically a few will move at much higher speeds over here on the graph. In a hot material, some particles will move at relatively high speeds right over here, but there will still be some particles that move at low speeds as well. So a material is not made up of uniform particles. Some will move fast, some will move slow. Temperature is the average of that speed, or really the average of the kinetic energy. Now, we in our everyday lives use two different scales for temperature. The first is Fahrenheit. We use this in pretty much every application in the US. Across the world, though, most countries use Celsius because it's based on the freezing and boiling points of water. 0 degrees Celsius is when water freezes, and 100 degrees Celsius is when water boils. But in this unit, we have to deal with temperatures where they go down to the point where particles no longer move, where they have zero speed. And that is not 0 degrees Celsius. Instead, we have to introduce a third scale called Kelvin. It has the same scale as Celsius, meaning that 1 degree Celsius is the same as changing by 1 Kelvin, but this is based on the point where all molecules stop moving. In other words, 0 Kelvin is when no particles move. Now, luckily, converting between Celsius and Kelvin is relatively easy. If we want to get to Celsius, we can simply take our temperature in Kelvin and subtract 273. Or if we have our degrees in Celsius, but we want to convert to Kelvin, we do Celsius plus 273. A quick hint is that remember that since Kelvin cannot be below zero, at zero everything stops moving, so you can't get lower than that. Your degrees in Celsius must always be lower than Kelvin because Celsius can become negative. And I'll show you two quick examples of temperature conversions. First, let's say it's a very hot day, that's 35 degrees Celsius, and I ask, well, what is this temperature in Kelvin? What you would do is you would take your equation, Kelvin equals Celsius, what you know, plus 273. I rewrote it here in black with 35 filled in for Celsius. Then you just add it up and it's 308 Kelvin. In example 2, I say the freezing point of nitrogen is 63 Kelvin, and I want to know that temperature in Celsius. We'll take your equation that says Celsius equals Kelvin minus 273, plug in your 63 for Kelvin, and subtract to get negative 210 degrees Celsius. Notice that is lower than our initial temperature of 63, so that should make sense. There's one more thing I want to go over here, and that's something called STP, or standard temperature and pressure. So standard temperature and pressure is something that is used across sciences and engineerings to say that it gives a standard point of where the temperature and pressure of a material is. Standard temperature pressure, or STP, is always equal to 0 degrees Celsius, or 273 Kelvin, and 1 atmosphere of pressure, and that's what we will use it as. However, oddly enough, you may find that other industries or other things you might study will say that technically this temperature could be a couple different ones. Some people use 25 degrees Celsius, some use 20. For us, we'll always stick with 0 Celsius, which is equal to 273 Kelvin. And that is all for the Unit 5 Section 1 notes, Part 1.